All right, ladies and gentlemen, we are going to start our physics lessons by talking about motion in one dimension. So in one dimension, we will be talking about motion along the horizontal, which is going to be our x-axis. And then we are also going to talk about motion along the vertical. I think that's how you spell vertical, which is going to be along the y-axis. Spelling is not my strong suit, so please be, kind. All right, so vectors and scalars. What's going on here? Okay, here we go. So definition that you need to know. A scalar is a quantity that has a value, which means a magnitude. So it has a numerical value, okay? You're going to see throughout the year that we're going to be asking what is the magnitude of the velocity, or what is the magnitude of the acceleration, what's the magnitude of the force. We're just asking for the number. Okay, we're asking for the scalar information. So in a scalar, the direction is not defined, it's not important, we don't really care about it. Okay, an example is speed. Speed is a scalar quantity. When you're driving around in your car and you look at your speedometer, it only tells you how fast you're going. It doesn't tell you what direction you're going. There's a separate piece of information that would provide that direction component. My car doesn't tell me what direction I'm going. It just tells me how fast. Fancier cars will tell you how fast, and then they'll have another component that tells you the direction. Okay. Other examples of scalar quantities are mass, temperature, volume, distance, and time. So all of those quantities are fully described just by a number. Okay. Next we have vectors. Vectors have a magnitude, which again means that it has a number associated with it and a direction. So vectors do take into account the direction. Okay. Examples are position, velocity, acceleration, and force. So when we talk about those concepts, those physics quantities, we're going to have to take into account which direction they're pointing. So signs will be assigned to them. They are either going to be positive or negative. That's how we're going to indicate the direction. By convention, motion to the right is considered positive, motion to the left is considered negative, motion up is positive, and motion down is negative. Generally, okay, motion to the east is going to be going to the right, so that will be negative. Motion to the west is going to be to the left, and that would be negative. North is going to be up, and then south is going to be down. I don't know very many physics teachers who want you to use your actual geographic location. Generally, right is east, left is west, up is north, down is south. And you assign your positives and negatives respectively. Oops, okay. All right, some other definitions. The origin is the point where variables have a value of 0. The terms position and displacement, those are used interchangeably, and they describe the separation between an object and the origin. They indicate the direction of movement. Position and displacement, they're the same thing basically, and they are a vector quantity. So the two arrows drawn from the origin to points represent a runner's position at two different times. So let's say this top arrow is at time 2 seconds, and over here, let's say 1, 2, 3, 4, 5, 6. Let's say that this is time 6 seconds. So it's just showing you that the position is changing over time. When we do diagrams in physics, we're not going to do fancy artistic diagrams. We're going to do very simple diagrams with little dots or squares to represent objects, which for people like me who are unable to draw is very helpful. Okay, so an object can have a negative position because it can be to the left of the origin, as it is here in this example. So in this picture, the runner is 5 meters to the left of the origin. So you could, if you were asked to describe the runner's position, you could do it 2 ways. You could say 5 meters left, or you could write -5 meters. Those two notations mean the exact same thing. By convention, this negative sign indicates left. I don't know what that was about. All right, some more terms for us. Distance is the total length covered during a trip. Distance is scalar. So distance has no direction. Okay? We don't care about the direction when we talk about distance. Displacement is a measure of how far and in what direction you are from a starting point. So displacement is a vector quantity. Okay? So for example, if you walk around a track and return to your original position, your displacement is 0, but your distance is 0.25 meters. So for example, here's your track, right? Your track is 0.25 meters around. Here's your start. Okay? If you walk from the start all the way around, you end up right where you started. That's where this 0 comes from. So your displacement is 0. You're right where you came, right back where you started from. But if we want to know how far you went, how far did you travel? You actually walked that 0.25 miles. So your distance is 0.25. Okay? It's kind of like when you leave your house and you go to school and you walk around the whole school all through your day, and then you come back to your house, your displacement is 0. So displacement doesn't take into account all that happened during the day. Displacement simply measures. All right, so here we are with our second example. It says Sally walked 200 meters east and 300 meters west. The total distance she walked was 500 meters. However, her displacement from her starting point is -100 meters. So let's look and see how we got those numbers. So I'm going to put a little circle here, and this is going to be where she started. Okay, so when we have to find the distance, okay, all we have to do is add each segment. Right? So distance is easy. We don't care about direction at all. So we're just going to do the 200 segment plus the 300 segment. That's going to give us the 500 meters. All right. Now, for displacement is different. Remember that displacement is defined as how far from the start, from where you started. So once her motion has ended, when she has stopped walking, she ends up at this red dot. So when we're finding the displacement, we are interested in the distance between those two red lines. Okay? So to calculate displacement, we're going to use an equation. Okay, so the equation we're going to use is delta x equals xf minus xi. Okay, this triangle is actually the Greek symbol delta, and it means change. The x is the physics representation for displacement, which remember can also be called position. Okay, xf is the final position or final displacement. I'm going to abbreviate so I don't run out of room. And then xi is the initial wayward dot there, or the starting position. Okay? So, if we look at where we started, we're going to call this x, this blue dot, that's going to be our xi. And we're going to say that she started at 0, because they don't tell us that she started at 10 and then walked 200. So we're going to say she starts here at 0 and goes 200 meters. So xi in this problem is equal to 0. xf is equal to this red segment. Okay, now to find the distance of this red segment that I've colored in, we're going to take her distances and subtract them. So she went 200 east. Okay, 200 east. Remember, east is positive. All right, and we're going to subtract, because we're going west, 300. So her final position, xf, is negative 100. So the change in position is going to be negative 100 minus 0, which is equal to negative 100. Remember that these negatives mean west. Okay? Yeah, so that's, it's kind of a little confusing, but with more practice, finding the displacement becomes much easier. So we'll do a few more examples. Those. Here's another example. All right, it says, little guy going around a track. The track is 100 meters around. So if the car travels once around the track, what distance does it travel? So we're talking distance. Distance means add everything up. So we start, we go around 100 meters. I'm going to change my pen color here. Number 12. So I got this from some worksheet somewhere. So if the car travels twice around the track, what distance does it travel? So now it's going around twice. So we're going to go around once, and then we're going to go around twice. So we got 100 plus 100. That's going to give us 200 meters. Okay. And then the last, I'm going to do purple here. The last part says the car travels once around the track. What is its displacement? All right, so here's xi. It's going to go once around the track and return back to where it started. So xi equals xf. So the displacement is 0. Okay, I think we got one more example, or two more examples, sorry. All right, so this one says, draw an arrow showing an object that moves from -4 to the -5 position. Well, that's not too hard. So we start here at -4, and we go to 5. Okay, so if we want to find the distance that the object traveled, we're just going to add them up. In this case, I would just count 1, 2, 3, 4, 5, 6, 7, 8, 9. So the distance that the person traveled, or whatever it was, is going to be 9 meters. Okay. Now, if I want to look, come on, pen, at the displacement, all right, I want to do change in position equals xf minus xi. Okay, so they tell us that we start at -4, so xi is -4 meters, and we end at 5. xf is equal to 5 meters. So the change in x is going to be 5 minus -4, which is going to give us 5 plus 4, which is going to be 9 meters. So in this case, because the object went in a single straight line, didn't turn around, didn't come back, didn't go in a circle, the displacement and the distance are the same. So that can be the case. It is okay to sometimes have the same distance and the same displacement. All right. Let's see here. Ah, yes. This would be our, oh, why is this? Okay. Anyways, all right, so here we go. A football player runs 35 meters east before realizing he's running towards the wrong goal. So maybe he's like 7, you know, like young kids do this all the time. He immediately changes direction and runs 23 meters west before getting tackled. All right, so let's start make like just a quick little diagram. Okay, so here we are. Here's position 0. He runs here, and here is 35 meters. Realizes he goes the wrong way and runs 23 meters the other way, this way. So from here to here, let me change the way I wrote that, is 23 meters. So here he gets tackled. So this position right here is our final position. That's where he's going to, the play, I guess is the word, is going to stop right here at this XF. So the first question, what distance did the athlete run during the play? Well, all we got to do is add, right? 35 plus 23 is equal to 58 meters. All right, excellent. Not too bad. The next question, what is the athlete's displacement at the end of the play? Well, we know that the starting position, the play started at point 0, and the play ended when the athlete was that orange line at XF, okay? So this is how far, this orange line represents how far the athlete is from the starting position. So to find XF, we have to do 35 minus 23, which is 12 meters. Now that we know X, so this distance right here is 12 meters. So now we can do change in X equals, that's not an X, XF minus XI. So 12 minus 0 is equal to 12 meters. All right, and there we have it. So don't be worried at this point if this displacement part is still a little fuzzy. We will get that ironed out in class and cover any questions that you might have over this stuff and do some more practice, of course. See you later. All right, guys, we're going to end today with the equation to find average speed. So average speed, I'm just going to call it speed. Most of the time when we calculate speed, we're going to look at average. So I'm just going to drop the word average. So speed is equal to total distance divided by total time. So you've probably seen this equation before. S equals d over t. That would be your equation. For your units, S is going to be in meters per second. D is going to be in meters, and T will be in seconds. Actually, those are like the standard units. You can use any unit of distance or any unit of time. I'm going to write this D over here because that meters. That line kind of took up the D space there. All right, so just remember that speed is a scalar, so it does not take into account direction. All right, and there you have it. And we will keep working on these types of problems for a day or two and then move on. I'll see you later.